Welcome. So in this video, I'll be covering another mode of heat transfer, which is convection. Convection is basically advection and conduction. Advection is related to molecular movement from one region to another region. And when molecules move from one region to another region and they collide with each other, they transfer heat by conduction. So convection is basically addition of advection and conduction. So now in this video, I'll be covering the concept of velocity and thermal boundary layer, and we will also understand the significance of some of the dimensionless numbers which are used in obtaining heat transfer coefficient. And once this knowledge is acquired, one can use these values which are obtained, namely the heat transfer coefficient, in designing the heat exchangers. So what is convection? As I told you, it is the mode of heat transfer in which we see appreciable movement of the molecules. And when these molecules move from one region, that is hot region, to cold region, or from cold region to hot region, they will exchange heat by colliding with each other. So we have a basic law, or the governing law for convection, which is Newton's law of cooling, which is given by heat flux equal to H into delta T. And this can also be written as H, which is heat transfer coefficient. It is also called as convective heat transfer coefficient, which is given in watt per meter square Kelvin. So heat transfer coefficient into surface temperature minus ambient temperature or surrounding temperature. So there are two types of convections. One is forced convection and second one is natural or free convection. Forced convection means we are using some external agency for forcing fluid which is exchanging heat with the surface, or which absorbs heat from the surface. But in natural convection, like if you have a hot body and if you place it in atmosphere, it will reject heat or lose heat to the surrounding naturally. And since we are not using any blower or fan, and we are not spending any energy, it is also called as free convection because we are not using any energy. So there are some correlations which are used for obtaining heat transfer coefficient. So three dimensionless numbers are used for obtaining heat transfer coefficient in forced convection. They are Nusselt number, Reynolds number, and Prandtl number. So these three dimensionless numbers, that is Nusselt number, Reynolds number, and Prandtl number, they are calculated using the mathematical expressions which we will be covering in the next slides. So these three dimensionless numbers, they have particular correlation, and using that correlation you can obtain firstly the Nusselt number. So Reynolds number is calculated, Prandtl number is calculated, and we know the values of C, N, and M. And using this correlation we can obtain Nusselt number, which is equal to HLC by K, where H is heat transfer coefficient, LC is the characteristic length, and K is the thermal conductivity of the fluid which is exchanging or removing heat from the surface. So these are three dimensionless numbers in case of forced convection. Similarly, you have three dimensionless numbers in case of free convection. They are Nusselt number, which is function of Grashoff's number, and Prandtl number. So again you have constant and some exponent of the product of Grashoff's number and Prandtl number. So firstly we need to calculate Greshoff's number, Prandtl number, and once you get Nusselt number you can just equate it with HLC by K and you get heat transfer coefficient. If you have values of thermal conductivity of the fluid, and you can also calculate characteristic length for a particular body. So once this is done, the H which is obtained in case of forced convection and natural convection, if you compare them, since we are using external energy and since the velocity is high, the heat transfer coefficients for forced convection, they are generally high as compared to natural convection. And here you can expect that the surface can be cooled in less time in case of forced convection as compared to natural or free convection, as the value of H is higher for forced convection. Let us firstly understand the concept of velocity boundary layer. So for that, let us assume that there is a flow over a flat plate. Assuming that the fluid is water, when it enters over the flat plate, at the leading edge you have velocity which is equal to free stream velocity, and as it moves over the plate, at the plate surface the velocity is equal to 0. This is called as no slip condition. Now if you measure the velocity in y direction away from the plate, you will get velocity, or you will see velocity to be increasing, and at one point it will be equal to free stream velocity. Now if I have free stream velocity as 100 meters per second, then at different location, if I measure the velocities at different values of y in vertical direction, you will get point at particular value of x where you will have velocity equal to 99% of the free stream velocity. So if u of fluid or velocity of the fluid is equal to 0.99 u infinity, that is free stream velocity, I get different points at different values of x. If I join those points, I will get a curve which is called as velocity boundary layer. So at velocity boundary layer you will have velocity which is 99% of the free stream velocity. Velocity of the fluid at any point on this velocity boundary layer is 99% of the free stream velocity. For laminar flow, since you have a fluid flow in specified direction, the thickness of the boundary layer is less. But when the flow changes to turbulent flow, there is mixing of fluid. The mixing will be from one layer to another, because of which the velocity drops, and because of this, the point at which you get 99% of the free stream velocity, or the velocity equal to 99% of the free stream velocity, that is much away from the surface. So the thickness of the boundary layer will increase with the increase in turbulence. But you have a region which is called as viscous sublayer, where the velocity or the flow is maintained. So that region is called as a viscous sublayer, where you have this velocity, free stream velocity, or the velocity of the fluid, which can be equal to free stream velocity. So that layer, small layer near the surface, is also called as a viscous sublayer. You can also say that at the velocity boundary layer, the fluid will actually feel the presence of the surface, but beyond that it will not, or the surface will not affect the flow of the fluid. So then the second So the next thing is thermal boundary layer. What is that? Let us again consider a hot plate over which there is flow of fluid, and let us assume that this difference between the temperature of plate and the fluid is 100 degrees Celsius. Just for the understanding, I am considering that the temperature difference is 100 degrees Celsius. So at the entrance you have fluid temperature uniform, but as soon as it comes in contact with the surface, the temperature difference between the fluid and the surface, it will differ. So like at certain location of X, at the plate surface the temperature difference is maximum. That means if you take the difference between the surface temperature difference between the surface and the fluid, it is maximum at the surface, but as you move away from the surface, the fluid which is passing over the surface will gain heat and it will get heated up. So this difference, it will go on decreasing and the layers will get heated. At the surface, the layer which is in contact with the surface will achieve temperature which is almost equal to the surface, but as you move away from the surface, the temperature will drop, and at particular location the temperature of the fluid, it will be almost equal to the free stream temperature, that is T infinity. So at different location, if I measure the temperature difference like surface temperature minus the fluid temperature, I'll get a profile like this. So wherever I get temperature of the fluid, that is difference between the surface temperature and the fluid temperature equal to 99% of the maximum temperature difference, that is Ts minus T infinity. So if I consider Ts minus T infinity as 100, wherever I get temperature equal to 99 degree, I'll mark those points at different values of X, and if I join them, I'll get a boundary layer which is called as thermal boundary layer. So again, because of the turbulence, the thickness of the boundary layer, thermal boundary layer, will be slightly higher as compared to laminar flow. So with this concept, now if you have understood what is velocity boundary layer and thermal boundary layer, we can now relate them using a dimensionless number which is called as Prandtl number. So delta, which is denoting the thickness of the velocity boundary layer, and delta T, which is denoting the thermal thickness of the thermal boundary layer, if I divide them, they are approximated to be equal to Prandtl number raised to some exponent. So they are function of Prandtl number. So this ratio you can equate it with Prandtl number raised to n. So what it means, if the thickness of the velocity boundary layer is less as compared to thermal boundary layer, then you can say that the Prandtl number is less than 1. What is Prandtl number? Anyways, we are going to see it, but then I'll just explain it. Prandtl number is the ratio of viscous forces to thermal diffusivity. So if the fluid is more viscous, then the value of delta will be larger. If the fluid has higher conductivity, then the thermal boundary layer thickness will be higher. So that means if the Prandtl number is less than 1, it means that the viscous forces are less as compared to the conductive forces or the diffusivity of the fluid. So the fluid which has high viscosity will have thick boundary layer as compared to thermal boundary layer, but the fluid which has higher conductivity will have thick thermal boundary layer as compared to velocity boundary layer. So when you say that Prandtl number is less than 1, you can say that the fluid is more conductive. And the another case is where you have Prandtl number greater than 1. There you can say that the fluid is more viscous and less conductive. So with this, we will now go through different dimensionless numbers which are used in analyzing the convection process. So first dimensionless number is the Reynolds number, which is given as inertia force by viscous force, and the expression for Reynolds number, almost all of the this is covered in fluid mechanics, so you know that this Reynolds number is given by rho v L by mu. This L is the length of the plate, or it can be considered as the characteristic length. For plates, it is the length along which the flow occurs. For pipes, it is the diameter of the pipe. So rho is the density, v is the velocity of the fluid, L is the characteristic length, and mu is the viscosity. So this Reynolds number, if it is higher, then we can say that the inertia is higher, that is inertia force is higher as compared to viscous force. If viscosity is high, then Reynolds number will drop because the velocity has dropped because of viscosity. So generally, if the Reynolds number is high, we can assume that, or we can say that the heat exchange will be more, and we can actually relate laminar flow and turbulent flow using this number. So generally Reynolds number is used in forced convection. There is another number which I told you earlier, that is Prandtl number, which is kinematic viscosity, that is nu by thermal diffusivity. So nu is related to viscosity of the fluid, and thermal diffusivity is related to the conductivity. So now conductivity to the heat capacity of the fluid. So if the conductivity is higher, then you have higher thermal diffusivity of the fluid. So in that case, the Prandtl number will be less. But if kinematic viscosity is high, then you will get higher values of Prandtl number. So Prandtl number is an important dimensionless number which is used in both forced convection as well as free convection. So let me show you some of the values of Prandtl number for different fluids. For liquid metals, this value is very less because the conductivity is high. So it is in between 0.004 to 0.03. For gases like air, it is in between 0.7 to 1. For water, it is between 1.7 to 13.7. For oils and glycerin, which are slightly viscous, this value is very high because the kinematic viscosity by diffusivity, that value will increase. So Prandtl number for this oils and glycerins is quite high. Then you have another dimensionless number, which is Nusselt number, which is given by Q convection by Q conduction, or conductive resistance by convective resistance, reciprocal of this two. So convective resistance or conductive resistance is B by Ka, and convective resistance is 1 upon Ha. Similarly, Q convection is H by Ha delta T, and the Q conduction is Ka delta T by L or B. So if you simplify this, it will be HLC by K, which L is the characteristic length, H is the heat transfer coefficient, and K is the conductivity. So for if you consider that the Nusselt number is constant, in that case H is directly proportional to the conduction. Similarly, the heat transfer coefficient is inversely proportional to the characteristic length. So these are some of the things which are related to forced convection. So Nusselt number, Prandtl number, and the Reynolds number, they are the dimensionless numbers which are used in forced convection. You can also write this relation between Nusselt number, Reynolds number, and Prandtl number using a single number, that is Stanton number, which is Nu by Ra into Pr. So this is just for simplification, which is used in forced convection. Similarly, you have another number which is called as Peclet number, which is product of Reynolds number and Prandtl number. This is also used for simplification. So here you can reduce it to VL by alpha, which is multiplication of Reynolds number and Prandtl number. So this is also related to forced convection. But there is another number which is called as Grashoff's number, is given by inertia force into buoyancy force by viscous force square. So if you simplify this, finally you will get an expression which is beta into G, that is beta is the volumetric coefficient of thermal expansion or coefficient of thermal expansion. So this term is related to buoyancy force. G is the acceleration due to gravity, delta T is the temperature difference between the surface and the fluid, L is the characteristic length, and nu is the kinematic viscosity. So G delta T L cube by nu square, this gives you Grashoff's number. And since this term has buoyancy term, this is related to natural convection, because in natural convection, when you have heat transfer, suppose you have a hot surface, the movement of the fluid is because of the change in density. So when there is change in density because of heating, when fluid comes in contact with the hot surface, it gets heated up, and it moves up because of the change in the density, or the movement is because of the change in density. So there we have a term which is called as coefficient of thermal expansion, and this is related to buoyancy. So this number is used in the natural convection. So you have three numbers which are used in natural convection. One is the Nusselt number, second one is the Grashoff's number, and third one is the Prandtl number. So these three numbers are used in case of natural convection, whereas you have Nusselt number, Reynolds number, and Prandtl number which is used in forced convection. So once this idea is cleared, then you can easily get the value of heat transfer coefficient. There is another term, important term in this calculation of dimensionless numbers, and that is characteristic length, which is denoted as L by L or LC. So for a flat plate, generally the characteristic length is denoted as L, and for a pipe or a cylinder, it is denoted as D. Now why this characteristic length calculation is important? Because you may have a geometry which is neither flat or circular. So for different geometries, you can actually use an expression which is 4AC, that is cross section area, by P, or you can also use characteristic length expression as 4AS by P, which is surface area by perimeter. So once you calculate this characteristic length, you can just substitute it in calculation of various dimensionless numbers, and those can be used for calculation of heat transfer coefficient. So for a flat plate, like suppose you have a horizontal plate, then you go for this expression, which is 4as by P. But if you have a vertical plate and there is a natural convection, in that case you need to use a vertical length of the plate. Like suppose plate is vertical, then the height of the plate will be the characteristic length. If it is horizontal, then the thickness of the plate, or using the expression 4as by P, that will be the characteristic length for the plate. If you have a cylinder, then, and if you have a natural convection, then in that case the diameter of the cylinder which is placed horizontal will be the characteristic length. But if that same cylinder is placed vertical, then the height of the cylinder will be the characteristic length of the cylinder in that case. But if you have forced convection, in which you are forcing fluid over the surface, then the dimension along which the fluid is flowing will be the characteristic length. So you need to remember this. Okay, this is all from this video. Thank you.